The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everybody. I'd like to welcome you to the first Seiler Glural Seminar of 2014. And I would like to introduce Craig Stowe to introduce our speaker.
Well, thank you. This afternoon, I'm very pleased to welcome Dr. Dale Robertson, who is with the USGS in Madison, Wisconsin. We've been trying to get Dale to speak here for a while because he's doing some work that's relevant to an awful lot of the other work that we do in the Great Lakes. And this morning, Dale said he actually spoke here before in the past, but it was about 25 years ago. So does anybody remember that? At the time, I guess, Dale was, well, Dale has a PhD from the University of Wisconsin in limnology and oceanography. And at the time, I guess he was doing models of lakes that were a lot more physically based. He was doing ice modeling and some other things that we talked about this morning. But this afternoon, it seems he's recently taken on models of more of an ornithological nature because he's going to talk to us about his Sparrow model. Perhaps some of you have been following the tweets that he's been sending out. I don't know. Actually, Sparrow has been a project of the USGS for a while now. I believe the first Sparrow paper came out, what was it, in Water Resources Research in 1997. This was Smith and Alexander and someone else, if I'm not mistaken. But it's been an ongoing USGS project for a while now. It's a model to a watershed-based model to estimate nutrient loads and changes in the watershed. And Dale has been for a few years now working on the Midwest version and the version that is relevant to the Great Lakes, and that's what he's going to talk to us about this afternoon. So I'm very pleased to welcome him to the podium.
Yeah, as Craig said, what I'd like to do today is sort of update everybody with some of the Sparrow modeling that we are doing, not only in the Midwest, but for the most part in the Midwest, and maybe a little bit on the Mississippi River Basin. Before I start here, I'd like to acknowledge my co-author, Dave Sade. Between the two of us, we've been working on Sparrow modeling in the Midwest probably for about the last 7 or 8 years. As most of you know, one of the most extensive problems we have in water quality in the Midwest, the U.S., probably the world, deals with excess nutrient loading, mostly phosphorus, nitrogen, coming in from the watershed, and it's causing all kinds of problems. As we look up here, we're seeing problems in the small streams, small lakes, but it doesn't stop there. It goes into much bigger systems like the Great Lakes. We're seeing here for algal blooms in Lake Erie, Cladophora on the beaches. Now with that, one of the things we're trying to do then is to really try to solve the problem. Most like consultants are doing. They're trying to go out there, find out where the nutrients are coming from, what the source of those nutrients are, and then try to do something about it. And when we look at that, most of what we know about nutrients really comes from lakes like this. This is Delavan Lake in Wisconsin. And we know, what's driving these algal blooms. We know it's nutrients coming in from the watershed. And with that, we can use various models like SWAT or HSPF, something like that, model the entire watershed, figure out where the nutrients are coming from, what the sources are, and go out there and do something about it. But as I showed, we also have problems at a much bigger scale. We got problems like Lake Erie, Gulf hypoxia, and so that's where it comes into looking for a different type of model. And that's really where Sparrow fits in. And so with Sparrow, we've got a few goals that come into almost all of our projects. The first one is to try to go out there and try to estimate loads over very large spatial areas. We're looking at SWAT. In general, we're talking about fairly small watersheds. But I'm looking at big watersheds. I'm looking at things, the entire Great Lakes, the entire Mississippi River Basin. The second thing that we do in a lot of these is trying to come up there and describe the loading in a way that we can rank things. So we can say this is where the bulk of the load is coming from. Here are the highest contributing areas. So we can rank those and people can take actions to try to fix the problem. The third main goal here is to try to find out the sources of those problems. It's not only important to mark where those sources are coming from, but we want to know what the source is. Is it something like point sources? Is it fertilizer? Is it manure? So that we can go out there and try to implement certain types of actions in the watershed. And finally, we're trying to provide information to others. And that's how I'm going to try to end this talk, is trying to show you one of the ways, or a couple of the ways that we're trying to provide the information from our models to various other people so they can go out there and use the information that we come up with. So what is SPARROW? SPARROW is a spatially referenced regression on watershed attributes model. And really what it is, it's a mass balance model in which we start off with a series of nutrient sources. And when we go through this, it's really important to get all the sources in the model. Because of how we develop this, if we don't get a source in there, we're going to get it in there one way or the other. So if we don't include in the source, it's going to probably creep into the other sources in the model. So what we do then is start off with all the nutrient sources. And in this case, we have fertilizer, manure, point sources, atmospheric deposition. And what we're trying to do when we develop this model is we try to get all those sources for a specific base year. So if you hear about a 1987 model or 1992 or 2002 model, what we're doing is we're referring to those nutrients for that specific year. So what we're going to do is we're assuming that that's sort of the conditions that are occurring right around that period of time. We're going to figure out how those nutrients that reach the surface of the landscape are transported through the rivers, and so we can match our estimated loads the best we can. Now when we do that, we don't put all the nutrients on at the same rates across the landscape. One thing else I wanted to point out, in addition to things like fertilizer, manure, we also have some models where we've taken that and changed those into crop types, like corn and wheat and that kind of thing. So depending on which SPARROW model you're looking at, you have to look at the sources that we're using, how we quantified all those nutrient sources. So like I said, one of the things we do is we don't put all those nutrients on and just assume they're all transported equally across the landscape. What we do is we allow that transport into the streams based on various environmental factors. It might be precipitation, soil types. And what we try to do is to find the factors, the environmental factors, as close as we can to describe that variation in delivery. This is very different than what like a SWOT model would have. The SWOT model has prescribed equations that are used in every model. We don't do that. We look for only in factors that are driving that variability. Once we have that, then we can predict throughout our entire landscape. In this case, the model is for the entire United States. So for this model, we can predict to 60-some thousand stream reaches. So it'd be like 60,000 stream gauges out there. What makes this model different than other models? Well, a couple of things. First of all, it separates land from in-stream processes. So what we do is we're going to figure out how the nutrients go from the landscape into a stream and then transport it downstream. And you may have heard about some of the applications of SPARROW, like down in Florida, where they're really looking at the in-stream processes, trying to figure out how much those nutrients are lost during delivery. Also, this type of model really is looking at, the one I'll talk about almost specifically today is a long-term equilibrium model. So if you want daily loads from a model like this, it's not going to get it for you. This is a long-term average, which has got its pluses. First of all, the minuses, it's only a long-term average. The pluses is that if we're looking at the entire U.S., we're looking at sort of like an average condition. So we don't have a storm coming through and might drive a part of the basin to contribute more than the average. This really represents that long-term average, and we can figure out what's going on the average. Once it's calibrated, we can interpret some of that kind of things. Some people try to go too far with that. What I try to do is to keep to the nutrient sources, and we try to use that to try to describe how important these various nutrient sources are to the total load. Where does SPARROW fit into all the kind of models that are out there? Well, models range really from the purely statistical to the more deterministic ones, and SPARROW sort of fits down the middle of that. We have sort of the artificial neural networks over to HSPF. SPARROW really tries to take advantage of both sides. We try to take advantage as much as we can with the deterministic side, especially with the sources, where we try to figure out how much of each of those sources are distributed downstream. We try to take advantage of more the regression type models, where we can put confidence limits, error bars on a lot of our predictions. So how does SPARROW work? This is just, I'm going to try to go through 3 of these, and hopefully one of these will make you feel better about how the whole thing works. Really the way it works is that we break the landscape up into a whole series of small watersheds. Not that different than SWOT. So if we start off here, and we start from the white area, a headwater stream, and work our way down, first of all, we estimate the load at that site by coming up with the load originating there, and I'll show you how we come up with that. And then we have a little bit of in-stream losses. For here, I've only chopped off half because we're looking at the whole basin. We assume only half of it is lost in the stream at any point by the time it reaches the end. Now if we work all the way down to the bottom, so we keep adding up all these little small watersheds until we get to the bottom. And then so we have all these ones up, those would be the headwater or the upstream watersheds, add in the lower piece, and then we have the in-stream decay. And so what we're trying to do is add all these things up, and so this would be to our first monitoring site. We might have 1,000 of these monitoring sites as we add up as we're going downstream. Okay. Here's my second of my versions of how this thing works. So here's this last watershed right here. You can see the dotted lines. So if we want to estimate the total load out of that watershed, we take everything that's coming in upstream, and then we add all those sources. So we're adding everything from fertilizer, manure, atmospheric deposition. We add it to the landscape, and then we transport it all. And if you're watching, I'm sort of developing this equation down below. And then we have a certain amount of in-stream decay as it's going down. Now the tricky thing for Sparrow is that we're going to try to get coefficients for each one of these things. So we're going to get a coefficient that goes with each one of these sources and each one of the landscape variables and ultimately in-stream decay. We're going to come up with those coefficients. Okay. So here's the math behind all of this. It's a pretty simple equation. If you think about all the pages that probably go into a SWOT model, this is it. We have one equation to describe everything in Sparrow. So what we do is we have the flux at any site is equal to the flux within the watershed plus that coming in from upstream. And we break that down into our sources, multiplied by a land-to-water delivery variable times in-stream decay. And then we just add those things up as we're going down. And so the tricky part here then is to come up with these calibration coefficients. So to do that, what we really need to do then is to have a whole series of flux sites. So we come up with those coefficients so that they work to minimize the error. And then all these GIS characteristics. So first of all, I want to describe this flux site so Song can figure out what some of these changes we were talking about earlier. So what we do for each one of the sites, we assemble this massive data set. So we might be looking at 1,000 calibration sites in the Midwest. For each of those, we have to have daily flows, and we have to have a whole series of concentrations. With that, anybody who's into the regression type computational loads sort of recognize this equation here, which is just saying for what we're going to do is try to come up with coefficients for A, B, C, D, and A, B, C, and D for that particular site. So we're going to have a whole as much data as we can assemble for that and come up with those coefficients. Once we come up with those coefficients, we basically multiply in log space. We're adding on the flow, and so we'll be able to compute the load on a daily basis. So what we might want to do here is compute the load for 25 years. If we have that kind of data, we'll come up with all that. Because what we want to do is come up with a long-term average load. Okay. So what we do then is after we're done, we compute it on a daily basis, add it up. We might come up with a curve that looks something like this. And each of this would be like 32 years of data, or 33 years of data coming through here, just connecting the annual loads. Compute on a daily basis, add them up. So when I was talking about a base year, well, here's the load in 2002. Well, it's a wet year. We really don't want to use that year because that particular area might have been a real wet part of the basin. Another one would be a dry period part of the basin. So what we really want to do is use that long-term average load. Okay? Now, if we did that for this particular site, they probably had a lot of things changing in the watershed over that. And we really don't want to come up with that long-term average load. What we really want to do is be trended for that site. Because what we're doing is trying to simulate what the conditions in 2002. We're trying to simulate the point sources, the management practices, all that in 2002. So the quickest way to show that is we do it a lot more, it's more sophisticated statistically. But the basis behind it is we do a regression through that, and that's the point that we would use. So we have 1,000 sites. For each of those sites, we're doing this to develop all of our calibration data set. So we start off with this really messy blue line. We end up with a real messy orange line. But what we're going to do is try to get that point where the orange line detrended crosses the base year. Okay? So by doing that, what we're trying to remove is all that variability that's out there. We're trying to remove it, but we're also trying to incorporate it. So we're incorporating wet years, dry years, all those kind of conditions that lead to the load at that particular site. Okay. So that's our sort of our Y variable in that equation. Now, all the inputs. We really have to get the sources down. If we don't get them, they're going to bleed into each other. So for our models, what we're trying to do then is come up with what's coming in from point sources in urban areas. So we actually went out there, and this is one of the major revisions that we have. I'll talk about that in a little while, is we spent a lot of time trying to come up with point sources for the area. Urban areas, for the most part, that's like a unit area load from urban areas. I'll show you that. Atmospheric deposition, farm fertilizers, fixation, animal manure, and then in some of these things like urban areas, we really don't have a number for it. So what we'll do is in the model just stick in the number of square kilometers of that particular land use and let the model come up with our best estimate of sort of kilograms per unit area. So those are all of our source terms. Then we also try to see how does that, what kind of characteristics of the landscape allow that delivery to vary. So we're looking at things like climate, soils, topography, tile drains. And what we'll do is we'll stick those in the regressions and try to find out which of those are important variables describing that variability in loads or yields from the basin. And finally, we have that transport term. And so we're looking at decay in streams and reservoirs. And in streams, we're mostly looking at a first-order decay. How long does it take for the water to get through a reach in the river? For reservoirs, how long is the water staying in that reservoir? So those are all the input variables for our model. So now if we go back, we describe the source terms, or the flux terms, which is what we're trying to match. Now we got all these GIS attributes. And what we'll go through is use a nonlinear regression now to come up with the best coefficients to describe what's going on in the landscape. Okay? Once we're done, we'll have that big equation. We can plug in all of our variables and describe everywhere in the landscape. So this is what was done back for a couple models, the 1987 model and 1992 model, and we're describing everything in the landscape. What can we do with that? I'll try to show you some of the outputs that we typically get from Sparrow models. First of all, we come up with loads, not too surprising. And this would be like having 62,000 gauging stations across that have a long-term average load, and we can describe what's coming in. So as you see the main rivers, those are the high loads, the sites with high loads coming in, low in the landscape, or low, high in the landscape. We can use that kind of information to get some real general kinds of things. So like for the Mississippi River, we can say that the highest loads are coming in from the Ohio River, followed by the central Mississippi, and we can sort of rank that kind of thing. So nothing too wild or crazy here. This is just sort of describing what's happening on the landscape. We can also describe sort of the incremental load, what's coming from the landscape and getting into the river. And this may be real important to a local community that wants to say, okay, if we look at that, which areas are losing the most nutrients? Not how much is getting to the Gulf of Mexico, but just how much is getting in to coming off the landscape. So we can use it for that. The other thing is that we know that once we get them into the stream, some get delivered a little more efficiently downstream than others. So if we looked at, let's say for nitrogen on the left here, you can see the darker colors, and if you look at that percent of the flux, it's really close to 100. What that's saying is if nutrients came into the main stem of the, in this case, the Mississippi, almost everything is delivered downstream. So if we wanted to get 1 kilogram lost into the Gulf, most of these on the main stem, you don't have to, almost all of it gets down. So 1.1 kilogram that gets in is going to get down to the base. But as we go upstream further, all the way up to the top, here now, like in the Missouri River, or let's say, pick any lake that intersects a river that you're interested in, a lot of it gets lost in that river, and so it might take 4 kilograms to get through. So what Sparrow can be used for then is to incorporate this, and the way we do that is in something that we call delivered incremental yields. So we have how much is coming from the landscape, but we can also look at how much does it take to get it all the way to the end of the basin. And so this is really important. If you're interested in, let's say, the Lake Michigan or the Mississippi River, the Gulf, and you wanted to say, how much do I have to reduce to get a certain impact? Now we can say, how much does it take to do that? And so if you have like a lake intercepting it, if you're on Lake Michigan and you have Lake Winnebago intercepting a big part of that load, if you're upstream of that lake, it's not going to have the same impact if you're right down near the lake, or down by the Great Lakes themselves. Okay. So what we can also look at this to say where are the greatest sources of nutrients, or to rank things. So when we do this, one of the first questions that I was asked to address was, we were looking at Gulf hypoxia, and they wanted to say, where are the greatest sources coming from? Well, that's really quick and dirty. All you have to do is take that incremental yields and break them down from 1 to, and this was done at a Huck 8 scale, and just rank them from 1 to 818. So that was really quick and dirty, and I could come up and say, here are the top 150. No big problem. The number one source of, in this case, is nitrogen. Is coming from some of these really big urban areas, with a lot of coming from sewage treatment plants and reaching down. And so when we started this, various states saw my results, and they were starting to get a little upset. I'm from Wisconsin, and they looked at this and said, okay, EPA is giving money out to reduce things. They're not going to get any money. So they were upset. Illinois came in here and said, wait a minute, every one of our basins in there? You don't give us enough money to address this problem. So what they wanted me to do then is, even before I had it out, they want me to put confidence limits on my predictions. So what we did was try to go through here and take advantage of the statistical sides of Sparrow. And so this line actually goes all the way out here. It stops at 200, but it goes out to 818. And so here's our confidence limits on this particular model. They're pretty wide, but we try to take advantage of this to say, how confident are we on some of our predictions? So if we looked at here, this one is ranked number 15 typically, but it really has quite a range in confidence limits on that. So you can see it could be somewhere between here and somewhere way out here. So what we tried to do then was develop an approach to come up with confidence limits. Yeah?
Your model is combined statistical regression model and physical and Basin model.
This is being broadcast, and they can't pick up your comments. Maybe we can hold this till the end, and then you can talk in the mic so everybody on the webinar can hear it.
Yeah, it'd probably be a little bit useful. But yes, it is. It's a mass balance model that has physical constraints on certain kinds of things, but we use regression techniques to come up with those coefficients. So it tries to take advantage of both sides of that. A little earlier I was showing you that it had this big mathematical equation, and so we go through that and we try to use regression techniques to come up with those coefficients. But we have certain mass balance constraints where we take these nutrients and pass it down. So I'll try to address it a little bit more as we go along. But so anyhow, we're trying to come up with confidence limits on each of those predictions. Well, when we come up and we use nonlinear regression, we come up with specific values for that, for each of the coefficients. But one of the questions was that, well, we're not really 100% certain on every one of our parameters we use, or every one of our values we use in there. So what we did then is we went through and weighted each of those observations a little bit differently and recalibrated the model. And so we did this a series of times. In this case, we used bootstrapping and did it 200 times and recalibrated the model each time. So on the first iteration, we went through, came up with this ranking, this value, and we used that to rank it. Then we weighted each of those values a little bit differently, recalibrated it, and made a new projection, and so forth. We did that 200 times. So this way we have like 200 different Sparrow models, all a little bit different based on how we weight the individual points in our regression. From that, what we could do then is you get a distribution of the ranks and give us some confidence on the ranks of those, and we can also get confidence limits on the how, in this case, we're trying to figure out how confident were we in the top 150 of those basins. So when we're done with that, now we had the confidence limits on the individual predictions to begin with. Now we also have confidences in the ranking values. And so from there, we could take that kind of input and, and now where we started off with this, which is the absolute ranking, we can go there and put confidence in it. So I don't want to get into this. It's sort of hard to read. It's pretty small. But what we came up with was 75% certainty that those points in this pink area were actually in the top 150. So we're able to come up with confidence limits in our Sparrow predictions and confidence limits in our rankings. So from here, now for the state of Wisconsin, they have a few of those sites where they can argue that they can try to get funding to try to reduce those. And also Iowa's starting to come in there and say almost all of our sites were almost as bad as Illinois is. So we can also use this kind of information to get to sources, because now if you look at that model, we have a specific, each of the sources, we can track that particular source through the whole thing and figure out those sources. And for the Mississippi, we're able to break it down. Like I was saying, when they developed, Rich Alexander and others made this model, instead of having fertilizers and manures, they had each of the crop types. And so for nitrogen, they came up and showed that corn and soybeans were the #1 source of nutrients. And for phosphorus, it was uncaptured animal manure. Newer models show it's a little bit different than that, and it's actually coming in to be fertilizers and manure driving that, and we're able to break that and describe that spatially. Okay, so with that, we have a national model to be able to describe everywhere in the landscape. Why would we want to ever go further? Well, first of all, any modeler wants to look at the residuals, and we look at that. What we really like to see is a general pattern, or no pattern. We just want to see it randomly across. Well, if you get into there and look close, well, I'm from Wisconsin. Almost every one of those are pointing up and saying we're over-predicting in that area. Iowa in that area is under-predicting those. which isn't really good when you're going to that small scale. So it's already saying maybe we should have regional models and try to describe things. In addition, if we look at the stream network that I showed you with those 62,000 locations, here's sort of the breakdown of the basins that we end up with. So like the Mississippi Basin is probably that one little point right there, the highest one. But we have a lot of real small basins. But if we looked at our calibration data points, they're up over here hovering around 10,000 as a median, 10,000 square miles, square kilometers. But our stream network is much smaller at about 500. So what we wanted to do then, both of those are pushing that maybe we should come up with a regional scale model with more data points for calibration. So what we did is in the NACWA program, we divided the country into 8 different pieces. And different people were in charge of each one. Dave Sade and myself ended up working on the upper Midwest. Steve Preston is coordinating all this effort. And what we tried to do, first of all, was come up with a new data set for this. So we went out, tried to get all the data from the USGS, from STORAT. When we took STORAT data, we only took the major sampling agencies, so we didn't get into a lot of problems with quality control. We thought we could minimize it that way. With that, look at our sites. Now we're not quite where we'd like to be. We'd like to be even lower, but we're much closer to the models that or the areas that we're predicting for. So instead of having 10,000 square kilometers, now we're down under 1,000 square kilometers. So we're getting closer to that scale. So we can not only have a better idea what we're doing there, so we think we're predicting there, but we can also look at our errors on that scale. Okay. We also went in there in the original models. If I went into the detail before, we're using population to estimate point sources. Now we went into the EPA database, the individual states, and try to come up with loads from each of the point sources. So we're trying to estimate our inputs to the model a little bit better. So now we have all of our fertilizer, manure, point sources, all of our inputs described for the Great Lakes. Here we're actually using a little bit bigger basin so we can get a little bit more sites for calibration, as well as the variability in the landscape. So we thought that's why we didn't just do it for the Great Lakes themselves. We have things like soil permeability, tile drains, all the environmental factors we thought would be driving the variability in the landscape. We're using an RF1 river network, and now we have about 800 data points to calibrate to develop this model for. So we put it all the way through, and now I'll really quickly go through the model itself. This is for phosphorus. We have 6 different inputs for sources: point sources, manure from confined animals, manure from unconfined, farm fertilizers, inputs from forest lands, and urban inputs from urban lands. So we have a description of all these kind of things that are coming in. Here's our coefficients that we came up with. I don't really want to get into those too much, but the only one I'll talk about is point sources. We really expected to see about 100% of the point source that gets into the stream having an impact. And when we calibrated the model, a 1 would have been a perfect 100%. We came up with a 1.07. So it says that we might be underestimating our point sources by maybe 7%, and the model wanted to beef that up a little bit. If you look at the p-values, they're all highly significant. For our land water delivery variables, we only end up with 2, soil permeability and tile drains. And what those are saying is that if you look at the signs on that, I don't want to go anything more than that, but in general, where the tile drains, we have more tile drains, you have a little bit less phosphorus delivered downstream. And I think that's what's saying is where you have more tile drains, you have a little less runoff occurring. In-stream decay and reservoir decay, I don't want to get into that too much, but we have that in the model also. Okay. And Song, this one's for you. We also looked at the root mean square error, and we do have an R-squared that comes out really well. So, inside joke, never mind. Okay. So when we're done with that, what we have is a description of what's coming off the landscape. The dark reds, maroons are the really high areas. In fact, these purple areas, if you looked at a few coming off, those are even higher yet. Those are this is for phosphorus, and that's the city of Chicago coming off, putting in a very high load right there. So if we look at that, we can get a description of what's happening. See the Corn Belt really well here, but we also have some high spots in Lake Erie, up on Lake Michigan, up around the Fox River, that'll compete with the Corn Belt very well. So with that, we were able to take that and estimate the total load to each of the Great Lakes. One thing that we did do in this is, we know that I'm a modeler, and I know there's residuals and all that, and so I tried to minimize that. Came back to haunt me a little bit. But I tried to minimize that by taking the estimated load at each of the sites and only use Sparrow to do the unmonitored area. Okay. With that, now we come up with the total load. We can come up with the yield here. And so if you looked at that, the load per unit area is the highest into Lake Erie. Not surprising, just looking at those colors, we could see that before. We can also break that down into individual sources where it's coming from. And it has basically the highest intensity of point sources in the basin. It's got Detroit, Toledo, and a few of those. Now when I show this, remember this is the entire basin from the U.S. side only. It doesn't include interbasin transfer, and it doesn't include Canada. So that's actually going to creep into one of my last slides. But we can describe what the nutrient sources coming into each one. And you can see these vary quite a bit. Lake Superior, mostly forest. That's where the bulk of its load is coming from. Lake Erie, mostly point sources, but also a lot of agriculture coming in. This is what threw a lot of people for a loop. If you just looked at point sources, we're coming up with numbers a little bit higher than a lot of people believed. Now this is 2002 inputs, you got to remember that. But we're coming up about on the high side of 40%. Still coming from the tributaries leading into Lake Erie. But this was 2002, and I really don't think things have changed that dramatically since then. We can also look at this, be very spatially explicit on these relative contributions. So if we look at this, now one of the things you have to remember, this I'm trying to show the percent of the total load in any specific area, and they always add up to 100. Okay? So some of these areas, you don't see it too much, but if I showed you for nitrogen, you'd see that atmospheric deposition in forested things were really high, but that's just high of a small number. So if we look at this, we can see where fertilizer most important, like through Illinois, way up in the North Dakota. Manure sort of coming through the middle, where it's the most important. Point sources, if you look at it, not too surprising around each of the urban areas. Obviously, that's where the point sources are coming in. So by doing this, we can not only describe where the loads are coming in, but now we can describe what the factors are that are driving it. One of the things I wanted to do next was to go in here and say, okay, can we use this to describe if things have changed or not? So we have our estimates. There's a study that was done back in 83 through 85 looking at that. But when the IJC did that, they were looking at things a little bit differently. They didn't have the total load to the lakes. What they were describing things were watershed loading, at least the numbers that I had that I could compare with it. So what I wanted to do is to adjust my numbers so I can compare with that study. And I simply took my total load, subtracted off the direct point sources from that, and it gave me a number that's a little bit more comparable. And so when we look at that, what we found is that the load to Lake Superior dropped, as well as Huron and Erie, and the other two stayed about the same. And we looked at some of our individual sites for Lake Superior. We saw that the load in the St. Louis dropped quite a bit, and some of these other tributaries that were pretty high, and some of these other sites followed what I'm showing here. With Lake Michigan, that sort of threw me a little bit because it hadn't changed, and I would have thought we would have seen a change. And so one of the things I wanted to do was to compare it with other studies. Well, here are the IJC numbers. These are unadjusted, so if there's been adjustments for atmospheric deposition, that's probably what's driving that. But if we look at that, there are the IJC estimates. The average, I did a study back a number of years ago, and mine came out to be pretty close to that, and that was just adding up the pieces. Very similar to what Dave Dolan had done. We had the mass balance study, and then here's my Sparrow estimates. And if you look at that, that seems to be right in line. And if there has been a change of loading into Lake Michigan, it probably occurred before a lot of this. So, and if we compare that with the target load of 5,600, if it stays that, we are quite a bit below it. But I got a feeling with the way that we're looking at things now with the nearshore shunting and things, that the new estimate of a goal is probably going to change. Okay. We can also use this to prioritize action. One of the things that we can do there is to try to look out very much like the Mississippi and say, where's the bulk of the load coming from? If we looked at total load, not too surprising, we'd say like the Fox River, the Grand River, that's where the bulk of the load is coming from, if we do it on total load. But another way to look at that is on yields. And right now I just did it on tributary, and we can see where the highest load per unit area is coming from. And those are the ones that if you want to try to come up with demonstration projects, these are probably the areas you want to pick because they have the highest load, the potential for the biggest change. We could also go through, I didn't show it here, but we could go in the Fox River using the individual Sparrow catchments and then rank those and come up with that. And we do have tools online that allow you to do that now. Okay. So we can rank it by, let's say, just Lake Michigan, or we could go through and rank each of the individual basins, whether it's all together or each one separately. Okay. One of the things we wanted to do then was just sort of see how does the Great Lakes compare with the other area. So I wanted to compare the other areas of the model, the Red River, the Upper Mississippi, and the Ohio River. Those are the areas in the Corn Belt you'd expect to be much higher. If we look at those yields, they're really not. Although you would have expected them to be, there's other factors that come in. And that's where we can come here. This is the percent of the total load, and we look at what's driving it. Although these have a lot of agriculture input, a lot of these other basins like the Ohio River, the Red River, they don't have the point sources like the small basins that the Great Lakes have. And so if we look at that, the Red River, strongly driven by fertilizer, the Upper Miss, fertilizer and manure, but they don't have the point sources that some of the Great Lakes have. So if we look at the total yield from those areas getting into the Great Lakes, it's not all that different than the Corn Belt. So that's where we are if we're looking in the past. We have also developed a few ways to look into the future, whether it's changes in land use or changes in climate. And to do this, the approach that we've termed it is called hydro-sparrow. And the reason why I called it that was really is that what we're doing is we're taking our sparrow estimates and we break it down into two pieces. We break it down to concentration and flow. So this is where the hydro part comes in. And we can look at that, break it down to those parts, and then try to see how, let's say, changes in land use might affect concentration. If they don't affect flow, we can multiply them back together and get it. Or if we change the flow, we can multiply them back and ultimately come up with new projections. So what we wanted to do then is say, okay, if we want to come through with this, we take our loads, break it down these two pieces, adjust one piece, multiply them back together, and go with it. So we've got two studies that we're doing this right now. One was with Meredith LeBeau and Alex Meyer from Michigan Tech. And we worked with Brian Pianowski from Purdue to try to say what can we project in the future if land use changes. And this is what Brian was working on. So we took that, and what Meredith did is she went through there. Here's Brian's output saying, well, if you look at this, we're looking for an urban expansion and then urban expansion with biofuel production. So we're looking at two scenarios. And so Brian came up with these changes in land use that we can expect in this case, 2040. And then we worked with Meredith to try to say, how would that change our inputs into Sparrow? If our population goes up a little bit, how will that affect point sources? If our agricultural land changes, how will that affect fertilizer and manure? And you can see they're not huge changes, so you're not going to see a big change. So Meredith came up and used those estimates to change our nutrient inputs. And then from there, we can make projections on how we expect changes in loading to look like. And so what we have here is the percent changed based on not only urban expansion, but also this biofuels production. And we see the reds are saying that in general, what we're going to see is that the loads are going to go up. Not a lot, but they're going to go up. And we see areas like around the city of Detroit, some of these other really big urban areas, the projection in the future is that the population will drop. So we expect those point sources to possibly come down a little bit. So that's not due to changes in sewage treatment plants. That's just saying that the population of Detroit is expected to drop as we go up to 2040. We can also, because of the way we're looking at this, look at each of the individual pieces and see how those are going to change. And so what we have here is looking at is the point sources, the urban areas, agricultural sources, forested areas, and the total. And so if we looked at Lake Michigan, what we see is the urban areas are going to go way up. Population is going to go up. It's going to have sprawl. We expect that to go up. Don't expect these bars to add up because this is just a percentile. But we expect that to go up. We expect the inputs from forested areas to drop a lot. Population is going to go in and start to go into these forested areas. But overall, we expect that change to be about 10%. And that would be an increase in loading. So that's what we're looking at in land use. We're also trying to make projections in this area for how climate might affect things. And to do that, again, we broke it down into two pieces. Now what we want to do is to take climate projections. So we're using downscale GCM output, basically driving changes in precipitation. So we have that for a whole series of GCM models. And we go through, input that into a PRMS model, hydrologic model, to see how changes in flows will go. Real quickly, PRMS, for those who haven't played with it, it's a very dynamic model, or a dynamic model with a lot of processes in it. And we're trying to simulate, by changing the weather, after we calibrate the model, we change the precip, the temperature, and try to see how that will affect stream flow. Then once we have the changes in stream flow, so that's our projected changes in stream flow over here on a fairly crude scale, but we have it for each of the basins. Then we start off with our concentrations, but we know the flow is going to change, so that should change our in-stream decay. So we altered our concentrations because of that little bit of a changes in decay. And then we multiplied them back together to get to our changes in loading in the future. Okay. So what we're doing then is taking one piece at a time. We know this is not exactly what's going to happen because this is assuming that the only change is that the overall annual flow is going to change. We're not looking at the intensity of small storms or big storms. Okay. This is just sort of that first cut assumption. One of the things we want to do now is to look at individual sites because we can do that based on our PRMS modeling. We can go to the mouth of the Fox, let's say, at the end of this, use the daily output and see if that agrees with what we're coming up with Sparrow. So we can look at the fine scale daily changes in precept based on the models and also look at this more crude scale and see if the two approaches agree. So that's where we're going there. We also have a couple other Sparrow models that we're developing in the upper Midwest. One is on the Assiniboine River. This is Lake Winnipeg, for those that don't know the area. We're working with the IJC, with some Canadians, to try to develop a model for that area. We're almost done with that one right now. We're also, as I showed you before, NACWA started off looking at 8 areas. We're going in the future. This was a 2002 model. A lot of people criticized us for being a little bit out of date. And what we're trying to do now is develop 2012 models with the 2012 inputs. Also, we're criticized for the scale. We're mostly at for the people that are into these things, it was like a Huck 11 scale. And what we're trying to do now is we're using, we went from RF1, now we're looking at NHD+, so we're going at a much smaller scale. We have to be a little bit concerned about how we project in the future because these are going to be pretty small basins, and we have to look at our inputs. A lot of stuff is based on counties, so we have to be not so much critical about the way we model, but how we show our results to other people, because we're going to be projecting down into sort of 1 square kilometer basins, and a lot of the stuff is based on much bigger scale than that. So we have to be a little careful with how we show the results. As we went there, we also sort of restructured. Instead of having 8 different groups, now we have 4. We have number 1, 2. Dave Sade and myself sort of grabbed a little bit. Now we've taken over the Mississippi and the Great Lakes, and so we're developing models for that entire area. And then 6, 7, and 8 are sort of merged together also. So Dave and I are continuing to work on the Mississippi, but we're also working on the entire Great Lakes. And when I say the entire Great Lakes, I really mean it now, because this is MRB3 that I showed you before, and we came up with results for the U.S. side. Now what we're trying to do is work with the Canadians. We're working with the IJC, or the NRC and the IJC, to come up with a truly Great Lakes Sparrow model. And so we're adding in everything north of the Great Lakes coming into here. We're working with them to come up with the point sources, the calibration data sets, so that we can really come up with a full-blown Great Lakes model. Right now, when we looked at Lake Erie, we had this small piece. We didn't have what's interbasin transfer. We didn't have what's coming in from the north side of Lake Erie. Now we really will have that entire basin covered. And we're hoping to have that model done, I think, in about the next 1.5 years or so. And just for terms, we're now calling that the Mid-Continental Sparrow Model. So we're getting a little bit more intense, a little bit wider, more encompassing. The last thing I wanted to go through fairly quickly is that, as I showed, one of the things we really want to do is to make our data available to other people. I do have links on here, but I'm not going to go through live links because it might take a little bit, but take my word for it, it goes pretty quickly, but just in case. So the first kind we have is, let's see, the mappers. These are sort of quick and dirty ways to see our results. You know, it's one that we're not trying to allow you to change anything, do any manipulations. This is really just to show you what we have for your specific area. And so we have 3 of these mappers available right now. One of them is for the MRB3 area. So here's our area. We can go through with a click of the button. We can change between phosphorus and nitrogen, and this shows you the entire. This one right now is showing you the accumulated. I can't see that. I think that's the accumulated load, so it's getting a little bit bigger as you get closer to the main stems. But that's showing you the load at any of those individual basins, and it'll gradually increase as you're going downstream. So that's what we have. We can click between those two. We can also change what we're looking at here. So let's say you're in the Midwest, but you really don't care about the entire area. Really what you care about is the Great Lakes. So you can go down here with a pull-down menu and either pick, you can pick your state, or you can pick your lake that you're interested in, or you can pick all of them. So here I'm picking the Great Lakes, and it very quickly cookie cutters out that area. You can get into a specific Great Lake. So in this case, we picked Lake Michigan, and it can show you those. We can also, down underneath here, it says group by, and so we can either show that by tributary, Huck 8, state. It's one of these kind of things that's really made for the EPA or your DNR, DEQ, where you want to go through here and look at where the loads are coming from. And so we can lump these in all different kinds of ways. In this case, right now, we're dumping them by tributary. And from there, if you looked over here, it says group by, and then there's 3 different little icons. One is a little histogram. And you can go through with that click, and it'll show you all the individual tributaries ranked from the highest to the lowest. And if you go over the top of any individual one, that it'll go on its outline so you can figure out who it is. And if you looked at that, it breaks down by point sources in each one of the individual sources coming in here. So you can break that down by tributary, by state, by Huck, and see those results. One of the things they also wanted more, this is something that was asked just recently. We were getting this from some people in Washington. They didn't want to make that one click to get to the Great Lakes. So now we have a Great Lakes mapper that automatically takes that one extra step and goes down. So, so you can break it down that way. You can also break those down by state. And so if you took out Michigan, you can see what the individual sources are coming into there. We also have another tool, which is a little bit more. This is more for the scientists. And what we have here is that we call it our decision support system. And if you go into there, this would be the first page you would see. So you get this, the U.S. If you clicked on any individual state, let's say you clicked on Wisconsin, it would isolate to only the models that are available for the Wisconsin. Then once you pick the model, you click over here, you can explore it, and you'll see the results for that particular area. So this is the MRB3 Sparrow model for that area. It clicks on that, and from here you can see all the inputs and the outputs from Sparrow. You can go down here with pull-down menus and see, let's say you wanted to see the point sources. You can see all that information. You can also download it. You can see all the inputs from fertilizer, manure, and get graphical presentations of those. You can also, if you follow, there's a little bar on here. So that was the displaying the results. You can go to Downstream Tracking. You can pick a site. Let's say you pick the mouth of the Fox River. You can go up here and only see the results for that particular basin. And again, we can see the loads. We can see all the inputs to that basin as well as all the outputs. So you can see all that. Now, if you went a little bit further, that was Downstream Tracking. Go to Change in Outputs, Change in Inputs. You can change your sources and see if I dropped out a sewage treatment plant, what would be the impact of that? And so if you clicked on that, you'd see each of your sources. And for the area you're interested in, you can change any of the individual sources by a certain percent. So you can take fertilizer and go from 100% down to 80% and see what your results are. So if you went through that, you can do that. It'll show you the final loads coming from those. It'll also show you a percent change. And so for here, I think I only changed point sources, and these are the areas that had point sources in it. You can also, when you're done with that, you can also look at it in terms of this are more graphical kind of things. Here, if you look at this is sort of before, after, and so forth. We just dropped the point sources out, so you can see the load. The inputs from point sources went from, I don't know, it's at 600,000 down to 0, and you can see how that would change the distribution of your inputs. You can also look at your changing your distribution of your outputs from here. And I didn't show it, but I have a table. If you went into there, you could also look at that and say how much of that could be a load reduction. If you're doing something like a TMDL, you can get into there and find out, did you achieve what you're hoping to achieve? For those who want to find a little bit more information when I'm done with this, the easiest way to find anything that I was showing you, at least for the Midwest, is just Google and type in USGS Wisconsin. That'll get to the Water Science Center webpage. And if you go down from here, this is the first thing that pop up. But if you look over here on the lower left, it says Sparrow. Click on that thing, and this page will pop up. And from here, you can go through here and get anything from background, online Sparrow tools. That'll get you the mapper, the DSS, those kind of things. You can go into here and find out what we have available for the Mississippi Atchafalaya River Basin give you the results there, the publications we have. MRB3 models, that'll give you everything in the upper Midwest. And now we have this other category now, the binational models. We're getting into the one for the red Assiniboine and ultimately the entire Great Lakes model. And then finally publications. Just want to mention a couple things. Almost everything I talked about today really was published in a paper that we did in 2011. That's this 2002 Sparrow model for the upper Midwest. Like I said, we're working on the newer one for 2012. Hopefully we'll be a few years down the track on that. Also, for anybody who's more interested, just outside the basin, we just published 2 more papers on the Mississippi River Basin. I know it's outside the Great Lakes, but I just want to mention it because it is so hot. This one just came out sort of I think last week. And so those are out there describing the sources as well as the ranking and why the ranking has changed to the Mississippi River Basin. So with that, I'll open it up for questions. Well, first of all, did I answer the question that you tried to describe? The question was, I guess, how do we use regression in this? It's more, we really start with a mass balance approach and try to get that. So we need to have all those sources in. So it's not just throw everything into a regression and whatever we get, we're done with it. Really, I look at this as it's a mass balance kind of model where we get these, and what we're trying to do is to get the coefficients that are the variables that make sense and use regression techniques then to come up with the values of those coefficients. So it uses regression to help calibrate it. That's just the approach we're using right now primarily. We're also talking, Song and I have been talking about trying to, and he's already done some of this before, instead of using regression techniques, use Bayesian statistics to drive this. Song's done a bit of this before, and we're hoping to look at that, well, we will be looking at that in the Great Lakes area, but that's still using the fundamental framework of Sparrow, but we're trying to calibrate it in different ways. Yeah, Joe?
Before I ask my question, I want to make sure that I say that I firmly believe that the best way to approach these kind of things is with multiple models that have different scales, different assumptions, and that sort of thing. And it seems like, based on your presentation, that the real value in Sparrow is at a larger scale, first of all, and if you apply it, say, decadally, like you're doing now, 2002, 2012, you could potentially assess what has been done in the watershed to change the loads over a period of time, at least on a larger scale. And you can use it for screening how things might change relative to land use changes, in terms of ranking the future. But my question is, SWOT and models like that are used very extensively to try to quantify the response of a given watershed to stated BMP implementation in that watershed. And also to identify where the BMPs ought to be, where you get the most bang for your buck in terms of BMPs. Can Sparrow be used for that kind of analysis, or not? Right.
Right. I guess the question is where does Sparrow fit into the whole scheme of modeling? I think that's the best way to look at it. And I completely agree with what you said, Joe. Sparrow is a big scale model, and it's great to describe the big patterns. If Sparrow did it all, I wouldn't be here for the meeting tomorrow. The meeting tomorrow is to look at small scale models and look at BMPs. Now with Sparrow, if you look at this map I showed here, and we wanted to say, here's sort of a hot spot right here. Now, what I really like to do is to go in there with more detailed models like SWOT, HSPF, and go into to look at that and see really what's going on. This is saying that this is where the high loads or yields are coming from, but it only gets you so far. BMPs, if we wanted to go through here, we have to fool the model to try to simulate it. So if we wanted to say, what is the effect of, let's say we go into some kind of BMP. We want a buffer strip, or a cover crop. What I have to do then is to go into the model and say cover crops have a 28% efficiency. So what do they affect? They're going to affect my fertilizer, manure, and this. I have to go into my inputs and change each one by that percent and then run the model. It's not a very good way, and I also have to rely on all other models to do that. Really what at that case, when you're trying to simulate specific BMPs, at least for right now, the best thing to do is to use a model that has it, like SWAT, to go in there and say, okay, I'm going to simulate these kind of things at that scale. The other thing is that, so yeah, I completely agree. The model, the same thing as if you want to go SWAT and you want to go a field level, that's probably not the right model either. You want to go all the way to apex. So I would say choose the model for what you're looking for. Sparrow's a great starting point to rank big basins, using it to, let's say, take the entire Mississippi River Basin and divide it in how much is coming from each state. How to implement actions to reduce some of those loads, I can tell you that fertilizer is the most important in this area, but how to reduce that, now you have to rely on other types of models. And that's where this is really a tag team kind of thing I think that comes in here. Sparrow is a good starting point. From here, I think there's other models that are much better than Sparrow at doing things. And whether that's SWAT or Apex, HSPF, whatever, that's really depends. One of the things that I feel uncomfortable about is whether I'm taking Sparrow and going too small, or whether somebody's taking a very small scale model and going too big. Like right now, I've seen people that use SWAT for the whole Mississippi River Basin. And if you look at that, the only way they can get all the inputs is they start to make assumptions like fertilizers applied on June 21st, well, I'd be pretty late, May 21st for this huge area. And then they're going to hit it with rain on one day. Well, really what happens is that fertilizers put on a whole series of days and rain hits it on a whole series of days. And so now you're trying to use something that's very process driven, but now you're lumping things. And so I think really what it's good is to keep the model what it's good for. Use Sparrow for the big things. Use something that has specific processes. If you're going to simulate the universal soil loss equation, you want to keep it to specific pieces. So use the model that fits. Yeah. Yeah.
So I'm curious, based on what you just said, if you're talking about setting down to 14 up, how are you guys going to treat that?
Right, and that's one of the things I was saying is be very carefully. If we're going to step down to a Huck 14. Now we're talking about something that's probably only a few square kilometers in size. I think this is a way to look at it. I think it's really up to me and people like me to be careful with how we show it. Because I can show a map just like this down to a Huck 14, but you have to realize that I'm driving it with probably county-wide fertilizer sales. I might not have the difference between a crop that's growing alfalfa versus one that's growing corn. One doesn't apply nitrogen, one does. And in the Sparrow model, I'm going to hit them both with the same amount. So you have to be careful with how you show your results. So I think as a first cut, it's probably good. But if people are going to get down to that level, it's going to be up to me to caution people on getting down to that. We'll do it, and it's the plus, though, is going down that small, is I can put the point source where it really belongs. I can put these things on a little bit better scale and describe it, but I still have, people don't like it. They always want that absolute ranking. I throw these big confidence limits up. Like I'll show this up, and I'll show that now in the Mississippi, Iowa's #1 for nitrogen. But within confidence limits, you have to be a little bit careful. It is #1. That's my best estimate that it's #1. But with confidence limits, I can't tell you that Iowa and Illinois are any different. So I think that you have to take both of those in there. Yeah, Jan?
So most of your presentation was talking about averaging loads.
Yep.
And I know NACLA's done quite a bit with fixed stations, so looking at loads and concentrations throughout the year. Are there other parameters that are predicted in Sparrow, or are you guys working on that, where you talk about 75th percentile loads, or base flow loads, or base flow concentrations?
Yeah.
It seems like there's a lot more that could be done with this framework.
Right. The question is that this is all based on long-term mean annual loading. And can we get down to the shorter kinds of things? We do have a certain amount looking at seasonality. and you input the load, and you can see what, if let's say you put in the entire source, I could develop coefficients that say this much is delivered in each of the seasons on average. Okay, so we could do something like that. The problem with this is that it is a mass balance model, and so it's, my own feeling is, although I've seen people try to do it, you shouldn't be looking at it in terms of base flow and high flows. Really, this is a high flow model. That's when the loads are occurring. So if you look at this, this is really the overall, so it really is a high flow model already, because it is the load that's coming through. In terms of changes from year to year, that's one of the things that's really being addressed right now. There's a few people that I've seen try to do it other places, but the one person I know that's doing the most of this right now is Rich Alexander. Rich Alexander is one of the authors of it originally, went back working on his PhD, and one of the things he's trying to do is go from year to year. He and Dick Smith are looking at a lot of this. They're the original authors of this. Right now, I think it's getting down to, they have an approach. I think they're still trying to encompass the statistics behind it. So they have some ideas with it. I think they're trying to get the statistics now to follow with it and come up with the approach that'll allow it. But what they're trying to do is, there's some that are trying to go from sort of decade to decade, which is one way. The other one is to go to year with carryovers and crops. And that, I know that Dick Smith is. I don't know if Rich Alexander's doing that also. I think he is. But they're trying to see how much is it left on a dry year would be left on the landscape versus on a wet year when it's all delivered. But that's something that they are trying to work on right now. I'm not working on it personally. I think I've got enough other things to jump in with my long-term equilibrium models.
And how about concentration?
Concentration, the one thing you remember, this is all volumetrically weighted concentrations. These are what we're working on. I've seen people try to use this for nutrient criteria. Personally, I know enough to know that volumetrically weighted concentrations and median or means are very different. I've got enough statistics behind the data sets we developed for this to know that that's not a good approach. This is really a volumetrically weighted concentration, and don't try to take that and extrapolate to a median. So.
I have some questions from the webinar.
Sure.
And please repeat them for them, like microphone's not working. How did you create your data layer for tile drain?
Oh, love one. Tile drains. We tried to. The question is, how do we develop the coverage for tile drains? We had two of them. One was from the NRC. It's a few years old. That was one that they estimated. There's also another tile drain coverage that I can't remember what university developed it, but they have one that was based on soil and crop type, and it came up with a regression saying this is where tile drains should be. We tried both of those in our models. The regression type model never worked very well because what it did is it said there should be tile drains in these areas and there weren't. And so what it did is if we try to calibrate on that, we had a really big residual because it said we had tile drains and we didn't have it, and it sort of backfired on us. So right now, as we're going from the 2002 models to the 2012 models, we're hoping to get a better coverage of that. And if the NRC has one, we're all for it.
Another question is, will Sparrow model sediment also, or just nutrients?
If you go, the question is do we have sediment models for Sparrow? Yes, we do have a national model. I don't really know how it works. I don't think it works that well. The problem with sediment and Sparrow is that small drainage basins can have a huge impact on this. And if you look at the scale we're talking about, we're talking a big scale. A few small drainage basins in an agricultural field or in an urban area will wipe it out completely. And so there's real problems. On these coverages, I think we're pushing 1 million reservoirs already. Not this model, but as we go to this NHD coverage, we're going to have 1 million reservoirs across the country. But if you can drive across the landscape and see a lot more detention ponds, and if you're going to model sediment, you're going to have to get each one of those models, each one of those in there. So there will be sediment models. I don't think they're going to do very well, at least not in the short term.
And one last question from the webinar audience. How is Sparrow able to determine the sources of phosphorus and nitrogen in a watershed when it doesn't appear to use inputs such as soil, land cover, topography, etc. in the model?
The question is, how does it come up with the individual sources if it doesn't have sort of a background concentration? Right now, the models that we have do sort of allocate it. It's when we say fertilizer and manure, both those numbers do incorporate the background that's coming off of it. So to only hit it, it's sort of saying that, well, the fertilizers we put down there year after year after year, what is background versus what's in the soil, it's hard to say. That's where we are in the past. In the future, we are trying to estimate that. We are trying to separate it out. We're going to have for people who know me, I've come up with various phosphorus zones which try to describe background concentrations in rivers and so forth. I tried using that as a coverage, trying to get that to come in. It didn't come in statistically significant, so we left it out. Now as we're going further, there is a coverage, and I can't remember who it's by, but it describes the background concentrations in streams. It's based on a whole series of samples that were collected in more what you classify as pristine streams, and they looked at these all across the country, and so we're trying to add that in to describe what would be coming off background. But right now, if you look at that, you have to look at those individual sources, and those are incorporated into those. So they are in there. It's just that they're not pulled apart. So if I say fertilizer and manure, you got to remember part of that is coming from the background in agricultural fields. The urban areas is a little bit more straightforward in that we don't try to break it down. We just have it. So the erosion that's coming off of urban areas sort of has that incorporated into it. Forested lands, we have that sort of in there because we have a forest term for phosphorus. It's really the agricultural terms that we don't separate what's coming off the background fields, but a lot of that was driven by fertilizers and manure to begin with.
Is there anyone else in the room that has a question?
Great.
Have you done any experimentation to let your estimated coefficients differ spatially on some kind of basis?
I haven't, but that is the approach that people we're trying to go right now. Right now, if you looked at that, we had 8 different models out there for the entire Midwest. When I developed the one for the Mississippi, the one that we developed, so that's the Mississippi, I took the approach where I didn't want to do that. I wanted to keep it sort of continuous across that. We do have an approach that Greg Schwartz developed where we can take and sort of regionalize these. You sort of start off with everybody gets this kind of concentration, and then different areas have deltas. So it starts off, let's say, a value of 0.32, and then we try to see if a delta for this certain area would be significant. We haven't done it yet, but it is something that Greg Schwartz has got an approach for that.
Any other questions? Okay, thank you very much.
I think they're both